Thank you. So this is a broad audience, so maybe I should remind you what Hamiltonian simulation is, and well, in particular, why should we care? So a famous physicist quoted that if you want to make a simulator of nature, then you gotta make it quantum mechanical. And indeed, broadly speaking, any problem that arises computation in any discipline of physics, including condensed matter, particle physics, atomic, molecular, optical physics, or even cosmology, may require a certain simulation of a model that mimics a real system. And it is hoped, well, it is, we envision that it will be useful for quantum chemistry problems to find the ground state energy of a certain molecule or stability of a certain configuration of arrangement of atoms. And surprisingly, the early algorithm to solve a linear equation using quantum computer uses Hamiltonian simulation as a subroutine. And you can think of a Hamiltonian simulation as a certain optimization problem when the problem, the solution of a problem is given as some ground state finding. So it has a broad applications, and many problems we care about can be formulated in terms of Hamiltonian simulation. And in this talk, it's not going to be, we're not going to cover all aspects of Hamiltonian simulation. We're focusing on a very particular one. So here's the problem. We are provided with a local Hamiltonian. For those who have worked on Hamiltonian complexity problems, this word might be confusing, but here we're using a physicist term. So local Hamiltonian is a local Hamiltonian in the Hamiltonian complexity problem theory, but it's a smaller class. So we're envisioning qubits laid down on some Euclidean, well, not necessarily Euclidean, but some metric space. And we we measure the distance between the qubits. And each term, each term in the Hamiltonian must be locally supported within some small size ball within that metric space. So in a Hamiltonian in the Hamiltonian complexity theory, you only care about the weight of each term, but here we care about the distance. And the goal of the problem is to output the time evolution unitary that I denote by U sub t, and it depends on the input Hamiltonian, and the t is some real parameter. In a particular case where this Hamiltonian is time independent, meaning that it is independent of t here, then the solution is going to be just the exponential of that huge matrix. Yeah, indeed. The Hamiltonian is huge as a matrix. It has an exponential size in the number of qubits. And we don't want to deal with that exponentially large matrix, so our output must be some efficient decomposition or description of this unitary. And as always, it is sufficient to produce certain approximation to that true unitary. And this is our goal. The problem setting should be clear at this point. Now, let me just repeat what is a local Hamiltonian, because not all of you are physicists. We envision some, more concretely, we envision some array of qubits. It can be arranged in a line or in a two-dimensional grid or a three-dimensional grid. And we build up the problem Hilbert space to be the tensor product of small complex vector space at each site. Here, site is just a synonymous to that tensor vector of small dimension. Usually, it's taken to be qubit, or for some problems, you may have to take some approximation to infinite dimensional, like a rotor. But for now, we're taking the finite dimensional complex vector space for each site. And the elementary interaction that governs the dynamics of the system is local with respect to the metric I'm drawing here. the three-dimensional lattice or two-dimensional or one-dimensional or any other metric space. And the Hamiltonian is simply the sum of such local interactions. Okay, that's the local Hamiltonian. Now let me emphasize once more and take my 1 hour of luxury to motivate, to reflect why do we care about this problem? Because they're fundamental. So this is one slide of history of physics. So Newton write down this formula, the Newton's equation, and the main contribution I see is that he separated the space-time trajectory from the force, and he declared that the gravity is described by this formula. There's a conceptual problem with this formula. This one, it just depends on the distance. So according to this formula, if the sun just evaporates right now, then the Earth will escape from the orbit we are currently going around. So there is no locality or notion of speed of light here. And then, similar but mathematically equivalent but much nicer description was given by Hamilton. And he decomposed this second-order differential equation to the first-order differential equation. And this is the formulation that we call Hamiltonian a Hamiltonian. And then Maxwell came along and realized that, there is some wave equation that governs the electromagnetism. And this one is conceptually very distinct from the Newtonian mechanics, because here we have a constant number that has a dimension of velocity, and we call it the speed of light. And this equation tells us that if the electric field changes at a certain point, then far observer does not observe instantaneously. It takes certain finite speed to observe that phenomena. Now, that's the advent of the special relativity. And indeed, Einstein wrote down his beautiful theory of special relativity based on the invariance of this special quantity. And here, the role of the speed of light is very important. And that's the foundation towards the world we see. And according to this formula, we now draw a space-time figure in this diagram. And then around the same time, a few decades later, the quantum mechanics has been invented. And there, the Hamiltonian has re-entering. The old formulation of Newtonian mechanics in some nicer way enters in a very bizarre way into an operator that acts on some complex vector space, which is conceptually very confusing, but that's why we are here. And almost 40 years later, some consistent description combining this quantum mechanics and the special relativity for the Maxwell equation has emerged, so-called quantum electrodynamics. And this describes almost all phenomena we see on Earth, because it's got the electromagnetism and all the electrons we see. And a few decades later, this continuous theory was written down as a lattice model, meaning that this continuous field theory inevitably involves some infinite dimensionality and some ugly infinities. The physicists knew how to handle those, but it's still confusing. And as a grad student, I was confused too. Maybe I'm still confused. But the lesson we were taught around this era, the Wilson renormalization group flow, the concept of that, told us that it doesn't matter what the microscopic theories are, as long as we care only about the long-range behaviors. And the main point, the main lesson for computer scientists is that don't be scared about this continuous theory. You can put the theory in some discrete lattice. You can talk about finite dimensional space, and that will well approximate the ultimate thing you want to understand eventually. So, and this is the world we view. I mean, in the sense that the current understanding is that all physical phenomena that happen in nature, we don't see any violation of the concept that everything emerges from certain local Hamiltonian that I defined just before, and every phenomena we see that does not well described by local Hamiltonian is just an emergent phenomena from that local Hamiltonian. So the problem of local Hamiltonian dynamics underlies the fundamental aspect of the understanding of our universe. So that's the reason why this problem is important. So you may ask, what about the quantum chemistry? Let me just recap. Quantum chemistry Hamiltonian is usually written in this form, in this first quantization form. You get some kinetic term and the potential interaction between the two. Oh, I forgot. Well, I must have erased that. There's a no lattice. So this Hamiltonian is not a field theory, and it is not a local Hamiltonian under our definition. But why do we care about that? Why? I just said that all phenomena emerges from some local Hamiltonian, but what about this one? The understanding is that this Hamiltonian emerges effectively for a long time scale and long distance time scale. Here, long compared to very tiny length scale, such as it's much smaller than the length scale of an atom. You have to dig much smaller to see the effect of those local Hamiltonian things. Once you go to the molecules, then all those effects are just washed away, and you're left with this Hamiltonian. So conceptually, any quantum chemistry Hamiltonian must be simulable by local Hamiltonian simulation. However, the required refinements of your space into a lattice may overwhelm your problem size. So practically, this is something you don't want to do. But the quantitative understanding is lacking. Probably I don't need the quantum circuit. Well, I don't need this slide, but just for the sake of completeness, I just include it. So quantum circuit is just a composition of small unitaries that are arranged in this fashion. And here, our gates are also local in the sense of we talked about the locality as before. So the total gate count is just a number of small unitaries, and the depth is going to be the number of layers, and each of the layers consists of non-overlapping unitaries. And the amazing fact is that each unitary can be chosen from this set of 3 elements. Nothing else we need. Okay, so coming back to our current problem, let me briefly review what has been done. So under the simple saying that infinitesimal time evolutions commute, that's the governing principle. And using that, Seth Lloyd put the formula that for Hamiltonians that consists of 2 or more terms, you can just decompose it into small time evolutions and just compose them, and that will well approximate the original unitary. This does not give you the best possible scaling as of now. And later, a higher order Schroeder-Suzuki formula was analyzed, and it gives a scaling of this form. It scales with the quadratic with respect to the space volume and the linear in the time you simulate, and has a polynomial scaling with respect to the air. And the one factor of space was recently dropped. And actually the dropped form, the almost linear algorithm in the space-time volume was claimed in 2014 paper where they studied the simulation of field theories, which is a local Hamiltonian simulation problem. And without such a locality constraint, if you just ask me to exponentiate an exponentially large Hermitian sparse matrix, then there are 2 major algorithms. One is based on the Taylor series that has a scaling of n to the square, where n is the number of qubits involved and the simulation time, and has the major breakthrough in this work is that the the error dependence is only logarithmic. And later, the so-called quantum signal processing technique was developed where the scaling is almost the same, but now the error dependence comes with an additive factor rather than a multiplicative factor. So that's the prior art before we wrote the paper. So here's our result. For any bounded local Hamiltonian, here bounded means that there is a uniform bound on the norm of the individual Hamiltonian term, local term, not the full Hamiltonian. On the Euclidean lattice, so we gave up arbitrary metric space, but just focus on the Euclidean lattice, the one-dimensional, two-dimensional, three-dimensional lattices. Then for any such Hamiltonian, we can write down the time evolution operator as a composition of elementary gates using only this much, the space-time volume multiplied by some polylog factor, where the epsilon is the approximation in the operator norm distance. The reason we don't specify alpha will be made clear later, so please bear with me. And for the case of time-dependent case, we need that each term must be efficiently computable. So it includes, obviously, the constant function, which is efficiently computable. Technically, by efficiently computable, we mean given epsilon and t in binary form, you should be able to output the term with the epsilon accuracy in polylog, both in time and accuracy. So the major tool for the algorithm will turn out to be amazingly simple. You'll be surprised and how simple this is. And the analysis involves so-called Lieb-Robinson bound. So let me tell you that. So I briefly went over the history of physics, and there the speed of light was put as a constant, just a given. But when you write down a lattice Hamiltonian, it is often not the case that you can write down the C in some consistent way. You have to make some approximation. But the amazing result is that as long as your Hamiltonian that you write on a piece of paper obeys that locality, then you can derive the corresponding quantity analogous to the speed of light. So technically, it reads the following. If I consider the Heisenberg evolution of some local observable, local operator, it doesn't have to be observable, by the Hamiltonian given, then as soon as I evolve a certain time, it acts everywhere. So it manifestly violates locality, meaning that you started with some operator, you evolve by Hamiltonian, but now it becomes a global operator. So I broke the special relativity for this matter. However, it does not act substantially everywhere. Quantitatively, this means the following. If I take the commutator of this evolved operator in the Heisenberg picture, and you bring another arbitrary operator that is supported on some other distant region, then the commutator between the two, if Hamiltonian obeyed the special relativity strictly, then if the separation between x and y were farther apart than the speed of light times t, then this commutator must vanish identically. However, this is, we don't assume that, so we don't know whether this is identically zero or not. However, we put in a strict upper bound on that, which is a pretty good one, and that reads, there's a decay in the norm of that commutator super exponentially in L. And there's a factorial factor in the denominator. So as long as the L is larger than some multiple of t, then it decays exponentially fast. So in other words, since By was arbitrary, let me explain the figure first. Since By was an arbitrary operator, I can probe the space profile of the evolved operator. And if I make a diagram or picture of that operator, then I would draw it like this one. There's a fuzzy region that I have completely no idea, just from this bound. But as long as you go out of that effective region, then the effect of this time-evolved operator decays super exponentially with the offset you go. Another version reads the following, which is actually more useful to us and probably more useful for you to use too. So I consider the time evolution operator as I wrote here. This is exactly this one. And I compare that with another time evolved operator, but with respect to a different Hamiltonian. Hamiltonian sub omega is just a Hamiltonian that consists of sum of terms that are supported within that region omega. So I just simply drop the terms beyond a certain ball. Then I compare the two, by comparison I mean look at the operator norm of the difference. Then that difference also decays super exponentially in the separation where the L is the diameter of this omega. So if you collect sufficiently many terms that would shield your initial operator AX at X, then that evolution by that operator will have an excellent approximation to the true evolution with respect to the original one. That's the meaning of this bound. This bound is very useful for one reason. It has nothing. It depends nothing but on the geometry of your lattice. It does not care anything about the detail of your Hamiltonian, just the locality. Here, the number zeta which I didn't define, it actually depends on the number of neighbors of a qubit and the upper bound, the uniform upper bound that we assume on the local terms of your Hamiltonian. That's all. So using this bound, we can now approximate the full, well, we can decompose the full time evolution operator, which is our goal. So I wish to approximate this operator. Now the time is going upwards. The space is the horizontal. Now I want to approximate this one. How should I do that? Well, the first guess is that I just divide the system into two halves, and then I collect all the terms supported on the left separately, and I collect all the terms supported on the right, and I evolve separately. Well, that's obviously wrong because this Hamiltonian may generate some entanglement between left half and right half, but this divided Hamiltonian will never do that. This is obviously wrong, but there's a simple fix. How should I fix that? Well, just cancel the wrong evolution and replace it with the original one. Yes, it is trivial. Now, let's look at the correction operator. Let's look at the correction operator. Well, I don't know how to analyze this. So the first thing I was told by my differential geometry teacher was that whenever you don't know, differentiate it. So I differentiate, and then, well, that will extract Hamiltonian factors from this red thing and the purple thing. The popped out operator here is a difference between the full thing and the sum of the terms on the left-hand side and some of the terms on the right-hand side. So the difference is just the terms that are connecting the two. Now they are localized. And I insert another resolution of identity, which is trivial to do. So far, everything is just equality. Now, this equation looks familiar. This operator, well, the operator in the middle is supported on the bridge, and it's conjugated by some local Hamiltonian evolution operator. And the Lieb-Robinson bound of the previous slide tells us that this is almost local. It decomposes it into operators, and the significant weight is all in the local terms. And this one and that one are identical. So it looks like a Schrödinger equation. Time derivative of something is equal to local operator times itself. So it is a Schrödinger equation. So it remains us to analyze this Schrödinger equation. How do we do that? Well, first, erase something that we don't want to see. So the object of interest is just this one. And the Lieb-Robinson bound tells us that how to approximate this one to something else. So here's the version we are particularly specifically using. The full time evolution is well approximated by a collection of Hamiltonian terms near that operator. So I can truncate that simply using this bound. Now it becomes approximate. Now this operator and the original this one is approximately the same. But if you look at this equation, this is again a Schrödinger equation, and whose solution is obvious because the form of the operator are the same. So I can just plug it in, the correct answer, without ever looking into any equation. This is a full calculation. You don't have to do anything else. So what have I done? I started with the full time evolution operator, made a wrong guess, corrected it, and then analyzed the correction part, and ended up with this truncated part. Now you look at the B part, they're the same, so we can just remove them. So here the approximation is only made when I truncated the bipartite Hamiltonian into the sum of terms that are supported near that boundary. And that's the only source of error in this equation. Now, what do? I just repeat it. So starting with the full, well, that was the iteration of the previous slide. And one good thing about this is that each block is a Hamiltonian time evolution operator of some local Hamiltonian. And the way to compute that local Hamiltonian is very simple. You just keep the terms within that block. No other complicated transformation. Well, I can approximate this bottom box using the same trick, but arranged on the opposite way. And I keep doing it. What I'm end up getting is the right-hand side. So for time evolved certain block, reversed in the half of the block, and then for time evolved the bridging part. And the approximation error in this decomposition will be epsilon as long as the overlap between these blocks is order L. And the L is logarithmic in that approximation parameter. So what to do with the higher dimensions? That was the one-dimensional situation. In higher dimensions, the things are similar. I just color the two-dimensional lattice into 3 colors. Why 3? Because it's convenient. Nothing special about it. I first forward time evolve these red blocks, and then I backward time evolve the intersection between red and blue, and then I forward time evolve the blue blocks. In that way, I obtain the complete time evolution for this union of the color 1 and 2, which was red and blue. And I'm left with the gray part. And I do the same thing. I just backward evolve the intersection between the gray and the previously done part, and I forward evolve the remaining part. And that way, I obtain the full time evolution in the full lattice. You can do the similar game for the 3-dimensional lattice, and there's a nice tiling using only 4 colors, and each cell is congruent to any other cell. So in general, if you can color your lattice with alpha colors, which you can always do using D+1 colors, then 2 alpha minus 1 layers per unit time is necessary in our scheme. Now the problem is reduced to implementing those small blocks. The small blocks are still large in a sense because it has unspecified size. So here's the recap. The block size has to be approximately equal to the overlap size, which is determined by the error you want to ultimately have. And that dependence is only logarithmic. And there will be around space-time volume number of blocks. And by the triangular inequality, the full error will be space-time volume times the error induced by each block. So each block has to be good to this much error. So we choose the block size to be the inverse of this vector. And the full gate count will be the number of blocks that follows from the Lieb-Robinson bound times the cost of implementing each block. And each block has size that is log in space-time divided by the accuracy. And we have to implement that block to accuracy that much. But there are pretty nice algorithms that gives you a polynomial dependence on the size and logarithmic dependence on accuracy. And we're done. So the picture that you might want to remember, a single picture, if there's a single picture that you want to remember, then it would be this one. So let me just remind you what kind of techniques can you use. This is not our work. I'm just reviewing what has been done. I really like this idea because it is unnatural. Whenever you see a unitary, you're supposed to multiply them. But here, this algorithm takes a linear combination of those. So the algorithm runs as follows. If you wish to apply this U unitary, which happens to be written as a linear combination of other unitaries, then prepare a state that is defined by these coefficients on some ancilla, and then implement certain controlled unitary that has nothing to do with this coefficient. And then you hope that these coefficients will be transferred to this control registers by starting with this one, and hope that you end up with the correct ancilla state. So abort if you succeed. This one doesn't always succeed, so you have to amplify the success probability. Essentially, it is a Grover search, but there is some ingenuous idea to implement this in practice. Yeah. And well, why this can be applied to Hamiltonian simulation? Because unitaries are complete basis for any operator as a linear space. And Hamiltonian is no different. And also, the time evolution operator, you can expand it, you can Taylor expand and truncate at a certain order, but the Taylor expansion converges exponentially. Well, actually, so it is good enough. Another idea is that so-called quantum signal processing, which starts with the same observation that any operator can be written as a linear combination of unitaries. But the idea is that this unitary can be inferred by another unitary that mixes up this coefficient and the controlled unitary. The transformation is a nonlinear function, but it's a good function, so you can manipulate. And that's what the so-called quantum signal processing does. You transform this unitary into the one you want. And you will have a chance to hear more about this idea on Thursday. And in practice, it uses much fewer ancilla, so you might want to use this one rather than the Taylor series approach. And it also yields a lower gate count because the dependence on the error is only additive. One big trouble for this approach is that it is unclear how to use this technique, the quantum signal processing, not the Taylor series, to the time-dependent case. Here we are inferring this Hamiltonian from this unitary, and it was crucial that the transformation only involves eigenvalues. But what are the eigenvalues for time-dependent Hamiltonian? It is ill-defined. So this is a problem. So we did some preliminary numerics, and the decomposition of the full time evolution operator for this antiferromagnetic Heisenberg chain with the field term compared to the previous algorithm, is not crazily complicated. The crossover point at which the asymptotically better algorithm wins over is around like 100 qubits. So it may be really useful. So now I'm talking about our algorithm is basically the best, up to log vectors. The first and very important observation, almost trivial, is that every circuit is actually a time evolution. Take any local unitary and take a log and exponentiate it back. So it's a trivial operation, but the log operator is a Hermitian matrix, a local Hermitian matrix, so we can regard it as a Hamiltonian term. So any circuit can be viewed as a time-dependent Hamiltonian, where the local terms are piecewise constant. Piecewise meaning that there's some order t division of the time axis in each of which it is constant. And the next observation is that circuit is very expressive. You can encode any function you want into a circuit. So we've divided one-dimensional line into chunks of qubits of size this much, log base 2 times t. So this technique requires you to consider that t is smaller than 2 to the n. Otherwise, the block size will be larger than the original system size, which is absurd. And you can implement basically any function in that column, in that bit. So multiplying all those, you see that there are doubly exponentially many such functions depending on the size of this k, but k is only logarithmic in t, so there are like 2 to the t such functions. And overall, you can express exponentially many such functions exponentially in the space-time volume up to log vector. And this counting, namely that there is exponentially many such functions that can be expressed in this form, remains to be true even if we require only one output bit. And the next observation is that how many parameters do we need to describe a quantum circuit? Well, we need to specify where the circuit element, the local unitary, is. So you need some index on the space coordinate. And when the gate is applied, so you need some time coordinate to specify when. And then what unitary do you apply? Well, there are only 3 choices. So overall, you need g times log vt parameters, where g is the total number of gates. And the number of all such circuits cannot be larger than exponential of these number of parameters. These are binary parameters, so. Okay, let's combine those observations. A depth t circuit on v qubits can express exponentially many Boolean functions, distinct Boolean functions. And general Hamiltonian simulation algorithm must be able to reproduce all circuit for computing every such function. And if you have a G quantum gates, then it can express only a space-time volume to the G different functions. So you get this inequality. So number of gates must be at least that much. And that is the gate count we are achieving. And one remarkable fact about this bound is that this bound works until the time is exponential in the number of qubits. So for all practical purposes and theoretical purposes, this is good enough. Let me tell you a little bit more about the bonus that we learned along this course. So overall, we decomposed the global unitary into small chunks and then used the off-the-shelf algorithm to implement those small blocks. But the off-the-shelf algorithms require ancillars. But what if the qubits are scarce? So yeah, this part is just a recap of what I have told you. All we need is that implementing that small block. But if I take the Suzuki-Schroeder formula to implement that small block Hamiltonian simulation problem, then that has a scaling that is polynomial in size, which is only polar logarithmic in the spacetime here. And the accuracy dependence is power law for some arbitrary small power. So you do immediately get an ancillary algorithm with almost optimal gate count, which does not directly replace the Schroeder-Suzuki decomposition, but it's almost the same. And many of you are interested in fermionic systems because that's relevant for quantum chemistry problems. And the first thing you would do when you encounter a fermionic Hamiltonian is that you replace any fermion operator into a Jordan-Wegener string. So for those who are not familiar with the fermions are just some operator acting on your Hilbert space, but it has a property that if they don't overlap, they anti-commute. That's all. So, and since we do not know how to implement such an operator on a quantum computer locally, we just take some representation of those operator, and this is a particular representation. So if we have a one-dimensional Hamiltonian, a fermionic Hamiltonian, then one fermion operator, a Majorana operator, will be represented by this string of product of string of z's, and another one will be represented by like that. And your local term in Hamiltonian will be a product of the two. So we take the product of these two operators and get another operator. In the one dimension, specifically, the product is always local, because the string structure conforms with the 1D lattice structure. But not anymore for higher dimensions. So think about two-dimensional grid. How can I represent this Jordan-Wegener string in this two-dimensional lattice? Well, I should forget the two-dimensional lattice and then pretend that I had a one-dimensional line that is sneaking through the system. Well, then, if I had a coupling term between these two sites that occupies that holds a fermion, then the corresponding operator will have a long string of z's that goes around this. This inhibits any parallelization you want to have. So this is a problem. But the solution was already given in quite a long time ago. So the first idea is that you throw in a few more fermions in such a way that if you modify a local Hamiltonian term using those additional fermion, then the resulting Jordan-Wegener string automatically cancel. So you end up with the local spin Hamiltonian, which faithfully generates the dynamics of the fermionic Hamiltonian, and the additional degrees of freedom that are fermionic is just frozen because they commute with the modified Hamiltonian. So you can do the fermions on lattices. And additionally, we obtain a new version of Lieb-Robinson bound for unbounded. Well, it's not unbounded. It's just that it's not uniformly bounded. So typical Lieb-Robinson bound requires you to have each term of Hamiltonian is uniformly bounded in operator norm. We relax that. We only require it is a finite number, and we don't care how finite it is. But we impose a condition on the commutator between the two terms, and it's upper bounded uniformly. And under that relaxed condition, we derive a bound that looks pretty much the same. The difference is that now the t factor here is multiplied by this commutator. Good thing is that if the commutator vanishes, in other words, if your Hamiltonian is commuting, then Lieb-Robinson bound gives you a zero error, which is trivially true. If your terms are commuting, then time evolution does nothing. It does not propagate anything. Yeah. This one improves upon the previous work where they had to assume that this Hamiltonian consists of two terms, each of which consists of commuting terms. And they put a bound on the commutator between the two. And we don't assume anything about that. So this one will improve our algorithm for a trivial reason. We have a better bound on the Lee-Robinson side. So our block decomposition may have a smaller size. It will give you the same error. Or you could, in some situation, you might want to evolve it for a longer time. If you naively did that, then this will give you a worse error in the Lee-Robinson side, but we have a better bound, so we can compensate that part. And let me remark that the algorithms using the idea of the linear combination of unitaries has nothing to do with the commutators. It does not improve even if your Hamiltonian is commuting. But our version, our tailored version for local Hamiltonians, improves. And by the way, the Chodo Suzuki, the good old one, knows about the commutator too. So here's a summary. The lattice Hamiltonian simulation is as efficient as possible up to logarithmic factors. And the overall analysis and the decomposition of the full unitary was derived by the Lee-Robinson bound, which dictates the speed of correlation propagation. And, and this decomposition is optimal because quantum circuit is basically the Hamiltonian simulation. So let me conclude with my conceptually important question. If you are given with the initial state that is an eigenstate of your Hamiltonian, what's the best algorithm to time evolve it? Is to do nothing, because it will not change. What if you are given with the Gibbs state? Well, it will not change, so doing nothing is the best. But all Hamiltonian simulation algorithm gives you a full access to the full Hilbert space, and it's either doing nothing or do the full thing. Can you interpolate between the two? That's my question. So with that, let me advertise our booth for a moment, and let me excite you with the news that we are giving out 5 Surface Gos. So just enter your name, and you're good to go. There's no other reservations. Okay, thanks for attention.
Okay, we have time for questions.
Thank you. This is probably really simple, but why did you use a hexagonal 2D lattice instead of a square bicolor 2D lattice?
Nothing special. It's just that the hexagonal lattice gives you a 3-color, whereas the square lattice will give you 4 colors, because the different colors should be well separated. Well, the same color cell must be well separated from each other.
So, so many results, previous results that have been proven by Lee-Robinson bounds. There's also then been alternative proofs using approximate ground state projectors or detectability lemma. I was just wondering, and then those have given better scaling in some parameters for, I'm thinking area law in 1D or other similar results. Is there any hope of, I mean, would you anticipate any improvements in some parameters using those techniques?
We have not thought about it, but my first guess is it doesn't, because for those Hamiltonians, they are pretty much maximally non-commuting. So.
Could you please go into more detail about the difference between quantum signal processing and cubitization, like the relationship between the two?
So Yeah, I was actually confused about the two words too. So quantum signal processing is a transformation from a unitary to another unitary, where you preserve eigenvectors, but you transform eigenvalues. Qubitization is a technique that refers to relate a unitary to another unitary whose eigenvectors are the same, but eigenvalues are different. The point of qubitization, well, which sounds similar, but the point of qubitization is that the qubitized unitary is much easier to implement than the original one. And then you use the signal processing to bring it back to the original one.
Hi, thanks for a great talk. So I had a question about the plot that you had that compared your scheme against Trotter for a particular toy model, just because. So I see that it's asymptotically optimal, but I'm just curious about what variant of Trotter goes into that, and whether it's the kind of analytic upper bound on the performance of Trotter you use, or this kind of empirical extrapolation that tends to be much better.
Probably that's the slide I'm not. I'm least confident about. So the data that doesn't use our Lieb-Robinson decomposition was taken from the paper by Andrew and others, and we did some optimization, but you should really ask Wang Hao, who knows all the detail about this simulation.
Okay.
Are there further questions?
So for the time-dependent Hamiltonians, why does it have to be slowly varying? Does it kind of violate the Robinson bound? Because in the original proof of the Robinson bound, I feel like it says nothing about slowly varying.
Good question. So the Lieb-Robinson bound really cares about the geometry only. So no matter how fast the term is changing, because a term is local, it can't really do much, even though the norm of that term is high. But when you use the Taylor series expansion technique to process that small block, you need to evaluate the functions at a certain point, and you wish that, and basically you're taking a Riemann sum for some integral. And the error for the Riemann sum is controlled by the derivative of that function you're integrating. So that's the source of the derivative.
Yes, please.
Is there any kind of analogy to a construction that would evolve in imaginary time to get close to a ground state?
Great question. So a lot of physics problem requires imaginary time evolution because we care about some static property, but there's a there's a complexity theoretic bottleneck to that. Even one-dimensional local Hamiltonian may have a QMA-hard ground state. So if the imaginary time evolution were easy, then that might contradict with that complexity hardness result.
As a follow-up, is there also a problem in that your circuit has to do a unitary evolution? I mean,
true. So in many places in our analysis, the unitaries is crucially used. Even in the beginning of the Robinson bound, you make use of the fact that the operator norm is invariant under unitary conjugation.
Do you have any ideas about how your algorithm could be extended to open quantum system? Let's say the boundary would interact with an outside system.
Simple answer is I don't know, but If you model, well, if you are simulating some Markovian channel, then there's a chance that, because it's after all some unitary evolution followed by forgetting. But otherwise, it's pretty much similar to the imaginary time evolution. So yeah, generally it should be hard.
So this method is for a quantum computer, but can you also formulate a version of it that's useful for people who are doing small system classical simulations, like with matrix product states?
Maybe. Well, our decomposition based on the Lie-Robinson is extremely simple. It's almost the fourth order Trotter formula, but except that the probably only difference is that the block size is increasing as the system size, although logarithmically. So you may able to achieve a better error scaling using this decomposition. It may be possible. Yeah.
Okay, thanks for the nice talk. So Felix has an announcement, so stick around for that. But first, let's thank Jungwon, and let's thank all of the speakers from today's session.